Okay, what we want to do here in Roman numeral 3 is find an inverse function algebraically. So there's that definition that we talked about previously, that a function that passes both the horizontal and vertical line tests is said to be one-to-one. If the function is one-to-one, then its inverse will exist, and the steps to find the inverse algebraically are to switch the x and the y and resolve for y, or just solve the equation for x if that makes more sense to you. Now, the other thing we're going to want to do is we're going to want to state the domain of the inverse. And so here's how we're going to do that. We're going to remember that inverses switch the domain and the range. And so what that means is that if I want to find the domain of the inverse, it's actually just going to be the range of the original function. So when we do inverse functions, the range of the original becomes, or really is the same as, the domain of the inverse. And so if I can think about what the graph looks like and determine what the range is, I'm going to be able to figure out what the domain of the inverse is. And so if we think about letter A here, we've got f of x is equal to x cubed plus 2. What would the range of that graph be? Well, if you think about what a cubic function looks like, a cubic function goes through the origin and has end behavior that goes down, all the way down, and all the way up, and therefore the range of that is going to be negative infinity to infinity. That means the domain of the inverse is also going to be negative infinity to infinity. So I actually just did the second part of this question first, and that's perfectly fine. Now, for finding the inverse, we want to switch the x and the y. Now, remember first that f of x is just another way to say y, and so if you want to start off with the first step being switching f of x for y, then by all means do that first. Then we want to switch x and y, so this is going to become x is equal to y cubed plus 2, and then I'm just going to resolve for y. So I'm going to subtract 2 on both sides. That's going to give me x minus 2 is equal to y cubed. And to get rid of a cube, I'm going to take the cube root of both sides. And so this is going to give me the inverse. I'm going to write it in inverse notation. So f inverse of x is equal to the cube root of x minus 2 with a domain of, again, because the range of the original was negative infinity to infinity, that is also the domain of my inverse function. Okay, letter B, find the inverse, state the domain for f of x is equal to the cube root of x plus 2. So again, if you think about what a cube root function looks like, it's just basically an inverted cube graph. And so the range of this original function is again going to be negative infinity to infinity, which means that the domain of the inverse is also going to be negative infinity to infinity. And so if I start off just by rewriting this as y equals the cube root of x plus 2, I'm going to switch the x and the y, so x is equal to the cube root of y plus 2. Let me erase that and try a little better here. Instead of x, we're going to put y there, and then I'm just going to resolve for y. So the first thing I need to do is get rid of the cube root, which means I'm going to cube both sides, and this will become x cubed is equal to y plus 2, and to get rid of plus 2, I'm just going to subtract 2 from both sides, and rewriting in inverse notation gives me f inverse of x is equal to x cubed minus 2 with a domain of negative infinity to positive infinity. Okay, letter C is going to be a little bit more complicated because it's a rational function, and so to find the range of this, we're actually going to find the horizontal asymptote. So the horizontal asymptote of this particular function using Bobo-Botten eats DC, I notice that I have an x over an x, and so that's going to give me y is equal to 1. And so the range basically is going to include every number except for 1. And so that's going to make my range of the original function negative infinity until 1, not included, and then not including 1 to infinity. Now, when I go to find the inverse, just like before, I'm going to just write f of x as y, and so this will be y is equal to x over x plus 1, and then I'm going to switch x and y so that this says x is equal to y over y plus 1. Now, my objective is to solve for y, and whenever I see a fraction, I want to try to get rid of the fraction first. And so I'm going to multiply this entire equation by the denominator, which is y plus 1. And so this is going to end up becoming x times y plus 1, which just to kind of keep things slow here, I'm just going to write that out, x times y plus 1. And on the right-hand side, the denominator is going to cancel, and so I'm just going to get y. Okay, on the left-hand side, I'm going to then distribute this x, which is going to give me xy plus x is equal to y. And now, because I'm trying to solve for y, I'm going to get all of the terms with y on the same side of the equation, which means I need to move this y right here over to be with this term that also has a y. And so that means I'm going to subtract it to the other side. And anything that doesn't have y, so for example, this x right here, it needs to move to the other side of the equation, which means it's going to become a negative x. Now, because both of these terms on the left-hand side have y in it, I can factor out a y from those two terms, and that's going to leave me with x minus 1 is equal to negative x. And the final step to get y by itself then is to divide both sides of this equation by that parentheses, x minus 1, so that the parentheses cancel, and I'm left with y by itself. And so I get y is equal to negative x over x minus 1, or in inverse notation, f inverse of x is equal to negative x over x minus 1, with a domain that is the same as the range of the original, which would be negative infinity to 1, and then union 1 to infinity. And just real quick, I want to just show you one thing that I think is really cool. Notice that the domain of the inverse corresponds to what the domain would be if I just told you, hey, find the domain of this function right here. If you were to find the domain of this, you would notice that there's a restriction from the denominator and that x cannot equal to 1, and that would correspond to the domain that is right there. And that's not a coincidence. That should happen anytime you find the inverse of a rational function. Okay, the last type of function that I want to show you how to find the inverse of is a square root function. And so once again, if we discuss the domain first, think about what a square root function looks like. This one has been shifted over 4 because of the minus 4 inside the radical. And so there's what the function looks like, more or less. Now, if we think about what the range of that is, the range is going to start at 0 and go to infinity. And so that right there tells me what the domain of the inverse will be, since once again, inverse functions switch the domain and the range. Okay, so finding the inverse, we're going to switch the x and the y first, and so this is going to become x is equal to the square root of y minus 4. In order to get rid of a square root, I'm going to square both sides, so x squared is equal to y minus 4, and then to get y by itself, I'm going to add 4 to both sides so that I get y is equal to x squared plus 4, and writing that in inverse notation, I'm going to have f inverse of x is equal to x squared plus 4 with a domain of 0 to infinity.